It seems like every day there's some new technology that's supposed to revolutionize everything, right? And you, being the curious person you are, want to understand what all the fuss is about without getting lost in all the tech jargon.
Exactly.
Well, today we're taking a deep dive into one of those really fascinating frontiers, the intersection of quantum computing and artificial intelligence.
Quantum AI, as it's often called.
Quantum AI, yeah.
You've got a really interesting collection of articles, research, even your own notes. You've been doing your homework.
I try to stay ahead of the curve.
It's really about trying to understand how these kind of bizarre principles of quantum mechanics, how they could actually change the abilities of AI as we know it.
And that's what we're going to try to unpack today, right?
Yep.
What's the potential here? Where do things stand now? And what are the biggest hurdles we still need to overcome?
Sounds like a plan.
All right, so let's jump in. What's the fundamental power that quantum brings to the AI table?
Well, it all starts with how information is processed. Classical computers, the ones we use every day, they use bits, which are either a 0 or a 1.
Right, the basic building blocks.
Exactly. But quantum computers, they use qubits. And qubits can be in this state called superposition, which means, get this, they can be both 0 and 1 at the same time.
Wait, hold on. How is that even possible?
It's a mind-bending concept from quantum mechanics, I know.
Yeah.
Imagine a coin spinning in the air.
Okay, got it.
It's not heads or tails. It's both until it lands. Qubits are like that spinning coin.
So it's not just a 0 or a 1, it's this blurry in-between state.
Precisely. And here's why that's a big deal. This both-at-once ability lets quantum computers explore tons of possibilities simultaneously. It's like massive parallelism on a scale that classical computers can't even touch. And that's where the potential for AI comes in.
So instead of going down one path at a time, you're exploring all these paths at the same time.
Exactly.
That's wild.
And then there's this other thing called entanglement. It's where two or more of these qubits get linked together. Their fates are tied no matter how far apart they are. You measure one, and you instantly know something about the others.
Spooky action at a distance.
That's one way to put it.
It's like they're communicating faster than the speed of light.
Well, it's not quite like that, but it's definitely counterintuitive.
Yeah, okay.
But the point is, this interconnectedness opens up a whole new level of exploring complex relationships within data.
I can already see where this is going. I mean, this could be huge for AI, especially when you think about all the computing power it takes to train these gigantic AI models like generative AI or those large language models we keep hearing about.
You're absolutely right. Training those models requires processing colossal data sets and finding really subtle patterns. It takes forever, costs a fortune, and uses a ton of energy. Quantum computing could potentially crack problems that are simply too big for even the most powerful classical computers to handle in a reasonable time frame.
And it's not just about speed, is it? You mentioned the energy consumption and the cost. That stuff matters in the real world.
It absolutely does. If quantum computing can lead to more efficient AI, something that can handle these massive data sets but doesn't need as much raw computing power, we could see substantial reductions in energy use and operational costs.
So quantum computing isn't just this thing off on its own. It's starting to team up with other advanced computing approaches.
That's a great observation. You see quantum computing being talked about more and more alongside things like high-performance computing and even edge computing. It's like this convergence of different types of computing power, all working together to tackle complex challenges in new and innovative ways.
Okay, so the potential is clearly enormous, but where do things stand right now? Are we talking about something that's years away, or are we actually seeing real progress in quantum AI research and development?
There's definitely tangible progress, and it's happening fast. On the hardware side, quantum computers are getting more powerful all the time. Companies like IBM and Atom Computing have already built machines with over 1,000 qubits.
Wow, 1,000.
Yeah, and while more qubits doesn't automatically mean better performance, it does mean we're moving towards being able to handle more complex computations. And we're actually starting to see quantum computers outperform even the most powerful classical supercomputers for certain specific tasks. It's what's often called quantum advantage.
So it's not just about having more qubits, it's about showing that they can actually do things classical computers simply can't.
Exactly.
What about the software side of things? Are there any real-world applications starting to emerge?
Yes, definitely. Quantinuum, for example, they've developed a framework for generative quantum AI, where their H2 quantum computer can actually be used to train AI systems and generate synthetic data.
Interesting.
And Rigetti, they've been working with government funding on a project where they used a quantum neural network to generate synthetic weather data.
Oh, wow.
The idea was to fill in gaps in radar coverage.
That's clever.
And they actually achieved performance comparable to classical methods. So we're seeing practical explorations of quantum machine learning being used to solve real-world problems.
And you mentioned that it's becoming easier for researchers and companies to actually work with this technology,
That's right. Cloud-based quantum platforms have made a huge difference.
democratizing access.
Exactly. It means more people can experiment with quantum algorithms and develop new applications. And another big focus is on improving reliability. Researchers are working on these things called logical qubits, which are designed to have much lower error rates than the physical qubits they're made from. It's a critical step towards fault-tolerant quantum computing, where we can do calculations without being swamped by errors.
So who are the big players driving this innovation? I mean, I kept seeing IBM and Google pop up in my research.
They're definitely key players. IBM has been instrumental in making quantum computing accessible with their quantum experience platform, and they're investing heavily in building next-generation quantum supercomputers. Google made headlines with their demonstration of quantum advantage, and they have a clear plan to build large-scale, error-corrected quantum computers.
Ambitious goals.
Very ambitious. Quantinuum is another company to watch. They're focusing specifically on quantum NLP and have a really aggressive roadmap to achieve fault tolerance by 2030. Microsoft is taking a different route, developing topological qubits with a long-term vision for quantum supercomputers. D-Wave is focusing on a special type of quantum computing called quantum annealing, which is really well suited for optimization problems. And then there's IQM quantum computers. They're working on simulation, optimization, and quantum machine learning, also aiming for fault tolerance in the next decade. This is a very diverse and competitive landscape.
Lots of different approaches being explored. Now, this term quantum machine learning kept popping up. Can you break down what that actually means?
Sure. Quantum machine learning, or QML, it's basically combining the unique power of quantum computing with traditional machine learning algorithms. It's about taking those quantum properties we talked about, superposition, entanglement, and quantum parallelism, and using them to potentially go beyond what's possible with classical machine learning.
So it's more than just running our existing AI algorithms on a quantum computer.
Yeah, it's a bit more than that. While that might be possible in some cases, QML is often about designing completely new machine learning models and algorithms that are inherently quantum in nature. A popular approach right now is using hybrid quantum classical models, where the quantum computer handles specific parts of a larger classical machine learning workflow, the parts that are really computationally intensive. It's about playing to the strengths of each type of computing.
Using the quantum power where it makes the biggest difference.
Exactly.
But it sounds like QML is still in its early days.
That's a fair assessment. The potential is huge, but many of the truly exciting applications are still theoretical. For example, there's a lot of debate about whether QML can consistently outperform classical methods when dealing with real-world digital health data. It highlights that quantum computing might not offer advantages in every situation, at least not yet.
Okay, so we've got this powerful quantum potential on one hand, and we've got the well-established world of classical AI on the other. How do researchers actually go about bridging that gap? How do they adapt classical AI algorithms to these new quantum platforms?
That's one of the big questions researchers are grappling with. A key area of research is the development of quantum neural networks, or QNNs.
I was wondering about those.
They're essentially quantum versions of classical neural networks. Those networks with interconnected layers of processing units that learn from data. But QNNs, they use quantum mechanics to do their thing.
And there are different ways to design these QNNs, right?
Right. There are data re-uploading classifiers. They're inspired by classical artificial neural networks, or ANNs, but they have this quantum twist. They take data and encode it multiple times into the quantum model, treating each encoding as a kind of quantum neuron. This repeated encoding allows the model to learn more complex patterns. Then there are quantum convolutional neural networks, or QCNNs.
QCNNs.
Yeah, those are particularly interesting for processing things like images or other types of data. They use these shallow quantum circuits, which are potentially well suited for the kind of quantum devices we have today. It's important to note that quantum models operate linearly within their mathematical space, which is different from classical convolutional neural networks, or CNNs. There are also these hybrid architectures where you combine both classical and quantum layers of computation.
Best of both worlds.
Exactly.
Yeah.
And there are even some researchers who are exploring using and training the actual physical controls of a quantum computer as a type of neural network. And there's even this prototype classification model that takes inspiration from the way quantum error correction works, specifically how it detects errors.
I remember reading that QCNNs seemed particularly promising for tasks like image recognition.
Yes, and in simulations, they've shown some really interesting results. For example, in high-energy physics, there's this task called top quark tagging. And QCNNs, in certain scenarios, they actually outperform classical CNNs in simulations. They can achieve this with fewer parameters, too. And there are techniques like dimensional expressivity analysis, or DEA, which are being used to optimize these QCNN circuits, basically finding and removing unnecessary parts without hurting performance.
What about other classical AI techniques like support vector machines? Are there quantum versions of those?
Yes, there are quantum support vector machines, or QSVMs. They use quantum feature maps and kernels to do their classification by mapping data into these higher dimensional quantum spaces. The idea is that this quantum approach could make it much easier to work with those complex kernel functions that are computationally demanding in the classical world.
And it's not just image data, right? There's work being done in natural language processing as well.
Absolutely. Quantinuum is actually working on basically rebuilding NLP techniques for quantum computers. This involves taking familiar NLP concepts like word embeddings, recurrent neural networks, RNNs, and even transformer models, and reimagining them for a quantum world. They even have a quantum transformer model called Quixer that has shown competitive performance with classical models on certain language tasks. Researchers are also exploring quantum tensor networks for NLP.
It's amazing to see how these fundamental AI building blocks are being reimagined for quantum computing. What about things like clustering and regression?
Quantum approaches are being explored there as well. For clustering, there are algorithms like Q-means that aim to leverage quantum properties to cluster large data sets more quickly and efficiently. And for regression, we're seeing quantum algorithms for linear regression that could potentially offer speedups over classical methods. There's research that suggests potential quadratic speedups for certain quantum algorithms in Gaussian process regression as well.
So much exciting work happening. Now, I also came across something called quantum-inspired algorithms. What are those exactly?
Those are really interesting. They're basically taking principles and mathematical techniques from quantum physics and applying them to classical computing.
Ah, I see.
The goal is to improve the performance of our existing classical AI systems without actually needing quantum hardware today. It's like borrowing the best ideas from the quantum realm to enhance our classical approaches.
Borrowing the best tools from the quantum toolbox. Okay, so we've talked a lot about the potential, but let's get real for a second. What are some of the major technical roadblocks on this quantum AI journey?
There are quite a few hurdles to overcome. One of the biggest is qubit coherence and decoherence. Qubits are extremely sensitive to their environment, and this noise causes them to lose their fragile quantum state.
So it's like trying to balance a house of cards in a windstorm.
That's a pretty good analogy. The noise limits how long we can do reliable computations, which is a major challenge.
So it's a race against time to get the computation done before the qubits lose their coherence.
Exactly. And then there's the issue of scalability. While we're seeing more and more qubits, scaling these systems up to the thousands or even millions that we might need for really complex AI problems while maintaining coherence and control, that's a massive challenge.
It's one thing to build a quantum computer with a handful of qubits. It's another thing entirely to build one with thousands or millions.
Precisely. And there's also the problem of crosstalk, where qubits unintentionally interact with each other. Plus, different qubit technologies have their own unique scaling challenges. It's not a one-size-fits-all situation.
And with such delicate systems, I imagine errors are a big concern.
Huge concern. Quantum systems are very prone to errors during computation.
It's like they're constantly tripping over their own feet.
Kind of, yeah. So quantum error correction is essential to mitigate these errors, but it's much more complex than error correction in classical computing. It often requires many physical qubits just to protect a single logical qubit. Achieving fault tolerance, where we can compute with arbitrarily low error rates, that's a really big goal for the field.
But at least there's progress being made.
Oh yeah, there's been some exciting progress recently in building nearly error-free physical qubits. That's a really positive step.
What about the challenge of getting all that data into the quantum computer in the first place? AI, especially machine learning, it thrives on massive data sets.
That's another big bottleneck. Efficiently loading large classical data sets into a quantum computer It's not easy. We need something like the quantum equivalent of RAM, what's often called QRAM, but it's still largely in the research and development phase. And some existing methods for encoding data into a quantum state are just not practical for really large data sets.
So it's more complicated than just pointing a quantum computer at a huge database.
Way more complicated.
Okay.
And then we have to figure out how to integrate these quantum systems with our existing classical computing infrastructure. Hybrid approaches are likely to be important in the near future, but finding the best way to split the work between quantum and classical systems and making sure they can communicate efficiently, it's not a trivial task. And let's not forget the impact of all that noise and those high error rates in the current generation of quantum computers. These so-called noisy intermediate-scale quantum, or NICU devices, they really limit what we can do with quantum AI algorithms right now. It restricts the complexity and the depth of the algorithms we can run reliably. And finally, there's a significant shortage of people with expertise in both quantum computing and AI. We need more people who can bridge these two worlds if we want to see this field really flourish.
So we're still in the early stages, figuring out the best ways to work with this new technology. Given all those challenges, what are some of the best practices that researchers are developing for actually designing and evaluating quantum algorithms for AI?
Well, even with all the hurdles, the field is making progress. One key area is the efficient design and optimization of quantum circuits. This involves breaking down problems into smaller steps, figuring out how to represent those steps, using quantum gates, and trying to use as few qubits and gates as possible.
So it's all about being clever and efficient with how you use the quantum resources.
Exactly. We need to leverage those quantum advantages, things like superposition and interference, really effectively. And when designing for AI inference engines, there are other trade-offs to consider, like how easy it is to train and deploy the model versus how efficient it is. Researchers are using techniques like tensor decomposition for optimization, and there's even work being done on using machine learning itself to help design new quantum algorithms.
Wow, that's fascinating. So AI is being used to build better quantum AI.
Yeah, it's a cool feedback loop. Another critical area is the careful allocation of qubits and selection of the right quantum gates.
Because the number of qubits and the depth of the quantum circuit, that all affects the overall complexity.
Exactly. And researchers are learning how to choose the right gates based on the specific hardware they're working with. Different hardware has different strengths and weaknesses.
And are there specialized tools to help with this intricate design process?
Yeah, absolutely. Quantum software development kits, or SDKs, and simulators are essential. Tools like IBM's Qiskit, Google's Cirq, Amazon's Bracket, and Xanadu's Penny Lane.
So those let researchers write, simulate, and test their quantum programs without always needing access to the real physical hardware, which can be expensive and time-consuming.
Right. Simulation is incredibly important in these early stages.
How do you know if a quantum algorithm is any good? How do you actually measure its effectiveness?
That's where benchmarking and rigorous evaluation come in. You have to compare the performance of your quantum algorithm against classical benchmarks using relevant data sets.
So you need a fair comparison.
Exactly. And as the field matures, we'll need more benchmarks that are specific to certain AI tasks. It's not enough to just look at how many quantum resources are used, like qubits and gates. You also need to consider the classical overhead, like the time it takes to load data and do error correction. And it's crucial to understand how performance scales with increasing problem size and the number of qubits.
So how does the algorithm handle bigger and bigger problems, essentially?
Exactly. Ultimately, for practical quantum AI, achieving fault tolerance through quantum error correction is going to be paramount, even if it comes with a significant overhead in the number of physical qubits needed.
Okay, let's get back to the big promise here. Speed. What kind of speedups are we realistically looking at for AI tasks when using quantum computing?
Well, the potential for significant speedups is a major driving force, as we discussed. Grover's algorithm, for example, it offers a quadratic speedup for searching unsorted databases, which means it could be much faster than classical methods for certain AI data retrieval tasks.
So if you're looking for a needle in a haystack, Grover's algorithm could help you find it faster.
That's the idea. And then there's Shor's algorithm. It offers an exponential speedup for factoring integers.
Factoring integers.
Yeah, breaking down numbers into their prime factors. It has huge implications for cryptography and potentially some AI optimization problems. It's important to understand the difference between a polynomial speedup and an exponential speedup.
Right, because exponential speedups, they're the game changers, right?
Yes.
They can unlock entirely new possibilities.
Exactly. But they're not guaranteed for all AI tasks, unfortunately. How much speed up we can actually achieve, it really depends on several factors.
Okay.
The structure of the specific problem, whether we have cleverly tailored quantum algorithms for that problem, the overhead of loading data into and out of the quantum computer, the noise in the hardware, and the scalability of the algorithm. There's no universal fast-forward button for all AI processes.
So it's not a magic bullet.
Not yet, anyway. And some of the theoretical speedups we see, they rely on very specific assumptions about the data. For example, some algorithms might work well if the data is very sparse,
Sparse.
meaning it has lots of zeros.
Yeah.
Or they might require access to special quantum data, or what are called quantum oracles, which are kind of like black boxes that can answer specific questions about the data.
Okay, starting to get a bit abstract there.
Yeah, it can get pretty deep into the theoretical weeds. But the point is, there's still a lot of debate in the scientific community about just how practical and achievable quantum advantage in AI will be. And it's likely to be very dependent on the specific characteristics of the data and how we manage to load that data onto the quantum computer.
So while we may not have definitive answers yet, are there any concrete examples where we're seeing these classical AI algorithms being successfully adapted to quantum computing, things that show real promise for the future?
Yes, there are some encouraging examples starting to emerge. We talked about the application of QCNNs to top quark tagging in high-energy physics.
Right, the particle physics example.
In simulations, they've performed better than classical CNNs, using relatively simple quantum circuits. And techniques like DEA have been very helpful in optimizing those circuits. We're also seeing quantum versions of the k-nearest neighbor algorithm for classification.
K-nearest neighbors, yeah.
Those are showing some theoretical advantages in terms of computational complexity. And there's research that shows improved performance on benchmark data sets, like linearly separable data and the MNIST handwritten digit data set, when you use multiple quantum data embedding strategies in quantum machine learning models.
So combining different ways of encoding the data into a quantum state can sometimes lead to better results.
Right. And there's ongoing work on quantum algorithms for linear regression that could potentially offer quadratic speedups without needing to adjust parameters based on the data. It's worth noting that many of these early studies have relied on classical simulations because of the limitations of current quantum hardware.
Right, because we can't run everything on real quantum computers just yet.
Exactly. So further validation on actual quantum devices is definitely needed. And the data sets used in these studies, like the JetNet library's top tagging data and MNIST, those are becoming important benchmarks for the field.
Okay, so it's clear that the theoretical potential is there and the simulations look encouraging. But the limitations of the current quantum hardware are still a big factor in actually realizing those benefits, right? How are those limitations specifically impacting real-world AI applications right now?
Well, the current limitations are holding us back in a few key ways. First, the limited number of qubits and their connectivity directly limits the size and complexity of the AI models and data sets we can work with.
So we're constrained by how much we can fit into the quantum computer.
Exactly. And the short coherence times, those mean that we can only run computations for very short periods before errors start to dominate. That puts a cap on how complex our AI models can be.
So it's like trying to build a really intricate sandcastle, but the tide keeps coming in and washing it away.
That's a great analogy. And the high error rates in the quantum gates themselves, those directly impact the accuracy and reliability of our quantum AI algorithms, as those errors tend to build up as the computation goes on.
So it's like a game of telephone, where the message gets more and more distorted as it's passed along.
Yeah, that's a good way to think about it. While we're developing quantum error correction techniques, those often require a lot of extra qubits, which further limits what we can do. And the lack of efficient QRAM, that makes it really difficult to directly port and speed up many classical AI algorithms that rely on quick access to large data sets. So the bottom line is that current quantum computers just aren't at a stage where they can run the large-scale complex AI models that are being used in practical applications today.
So there's still a long way to go.
There is. And on top of all that, there are still some major engineering challenges in simply scaling up these quantum systems for widespread use. Things like maintaining the extremely controlled environments and ultra-low temperatures that many qubit technologies need to function.
Right, quantum computers are still very delicate and require very specific conditions to operate. Okay, so looking ahead, what are some of the future trajectories and potential breakthroughs that could really unlock the power of quantum computing for AI and help us overcome all those limitations we just talked about?
The future is actually pretty exciting. We're seeing roadmaps from leading companies like Google, Microsoft, and Quantinuum that are aiming for much larger scale, fault-tolerant quantum computers, potentially with millions of qubits.
The millions of qubits.
Yeah, it's hard to even wrap your head around. There's a lot of focus on developing more stable qubit technologies. Things like topological qubits and diamond-based systems, which are inherently less sensitive to noise. And we can expect to see significant advancements in error mitigation and error correction techniques, which will be absolutely essential for increasing the number of usable qubits and enabling us to do more complex computations. The arrival of fully fault-tolerant quantum computers with logical qubits, that's going to be a game changer for quantum AI. It'll finally unlock the potential of many of the algorithms that are currently limited and allow us to explore much more sophisticated quantum AI models. And there's a lot of promising research happening in emerging areas.
Like what?
Well, there's generative quantum AI.
For creating synthetic data to train classical AI models, right?
Exactly. And then there's quantum enhanced machine learning, or QML, for achieving better training and overall performance, especially for optimization tasks, which are central to so many areas of AI. We're also seeing the development of new quantum algorithms specifically designed for various optimization problems in AI, as well as quantum natural language processing, which could significantly advance our capabilities in language understanding. And here's a really cool twist. AI itself is expected to play an increasingly important role in advancing quantum computing.
Whoa, so AI helping to improve quantum computing.
Yeah. AI could help us optimize quantum error correction protocols and even develop more efficient quantum algorithms. And the role of hybrid quantum classical computing, where we combine the strengths of both paradigms, that's only going to become more important in the years to come.
So it's not just about replacing classical computing with quantum computing. It's about finding the best ways for them to work together.
Absolutely. And just to give you a sense of the timeline, companies like Google are aiming to have logical qubits and eventually large-scale error-corrected systems in the next few years.
Ambition.
Microsoft is taking its own approach with its hardware-protected qubits and is working towards resilient quantum systems that will eventually lead to quantum supercomputers. Quantinuum has an accelerated roadmap targeting universal fault-tolerant quantum computing by 2030. And IQM has milestones for improving the performance of their quantum gates, introducing new error reduction techniques and developing larger error-corrected systems, all aiming for early quantum utility in areas like QML and optimization. They're also aiming for fully fault-tolerant systems sometime after 2030.
That's a lot of progress in a relatively short amount of time. This has been a truly fascinating deep dive into the world of quantum AI. So to summarize, it sounds like quantum computing has the genuine potential to dramatically speed up and enhance artificial intelligence in some really fundamental ways.
It really does.
We've talked about the different approaches researchers are taking to adapt classical AI algorithms to this new quantum world. And while there are definitely significant technical challenges that need to be overcome, the future direction and the potential breakthroughs are incredibly promising.
I totally agree. This is a field that's full of potential. While it's still early days, the progress we're seeing and the strong theoretical foundation really suggests that we could be on the verge of something truly transformative, something that could revolutionize both computing and artificial intelligence.
It makes you wonder, doesn't it?
It does.
I mean, with the incredible pace of innovation we're seeing in both quantum computing and AI, what completely new applications or even totally unforeseen technological revolutions might emerge when these two powerful forces fully converge? Just something to ponder. Thanks for joining us on this deep dive.
It's been a pleasure.
I always learn something new.
Me too.